Okay, so welcome back to lecture 17, and today's lecture is an extension or like part 2 of reinforcement learning that we started last time. Let me bring this up. Yeah, and today's session is completely online, so if you have questions, you can just like go ahead and ask in the chat window, and I'll try to come back and answer those as much as I can. If you're not able to hear me, let me know in the chat window and I'll try to do something, at least try to fix that. So coming back to today's lecture, it is about a Bellman expectation equation. So a quick review of what we said last time. There were two equations that we came up with, and those are together known as the Bellman equations. And precisely what they were telling us was there is this value function. So if you remember, reinforcement learning is another paradigm of learning in which like an agent is interacting with the environment. And as the agent moves from one state to another, they are deriving some value by taking that action. So we defined a value function, which was nothing but an expectation of the total returns that you get like in any time step t. It's a very simple equation, just calculate the expectation of this, which was nothing but the rewards that you're getting at every time step. And it depends like what type of problem we are solving. Let's say it's an infinite horizon problem. Then like we sum it up to infinity and then do something with that series. If it's a finite horizon problem, then you can just like take the final time step and accordingly just like change the summation. But having said that, the thing that we're going to focus on today is the recursive property that we came up with here. Because if you remember from the previous lecture, I said that uh, reinforcement learning is a different paradigm of learning in the sense that we are not finding any classifiers, we are not finding any clusters, but rather we are solving this optimization problem. And if we can get some nice form to this optimization problem, then excuse me, if we can get some nice form to this optimization problem, that becomes easier for us to solve. So we were talking about these Markov decision processes, and based on that, we came up with this. So today, what we are looking at is a way to solve these Markov decision processes using dynamic programming. So more specifically, we will look at Bellman optimality equation for state value function, Bellman optimality equation for state action value function, which was the Q function. And I'm going to repeat all of that, so don't worry too much. But just remember that like the state value function or sometimes the value function is telling us what value are we deriving from being in state S. State action value function is telling us, given we took action A, what is the value we are getting when we are like in a state S. So that's the fundamental difference. So I will begin with Bellman expectation equations. And as you can tell from the definition of expectation itself, that just involves like probability values, right? So let me just like write it down first so that we are on the same page. And remember, we came up with a more simpler notation than what we have here, because what we have here is like I directly picked it from the textbook, and the link is provided in the reference, so you can pick that up from there. But like just to give you a review of the previous lecture, mathematically we can write the expectation equation or the Bellman expectation equation as something like this. And this is like the simplified form, right? So the value under policy pi state S is the expectation that you're getting over this, like following this policy over RT plus 1. And if you remember, R was for the reward that I'm getting for in any time step, right? In state S, plus the discount factor. Remember why we had the discount factor? It has to be between 0 and 1. And because like we are trying to anticipate the rewards in the future steps, that's why we have that. And then the value function, the same value function for step S plus 1, given we are in state S. This is what we defined last time, right? So this is the Bellman expectation equation for my state value function, which is like V of S. And similarly, I can have like another equation that was the Q function that was nothing but like telling us how much value can I get when I take this action. right? So we said there are two things. One is that we are not considering my action, the agent's action, but now we are considering like the agent's action. And so I had the Q value. And this Q value will stay with us because we need it. And so that's why it's a function of S, like I'm in state S and action A, right? So again, this has a recursive form, which is good for us because it's an optimization problem we are trying to solve. And the way it's like related, and I'll talk through these terms again. Discounted value Q sub pi S t plus 1 A t plus 1. I'm going to talk through all of this given I am in state S and given the action that I'm taking is A. Okay, I see a lot of people joining just now, and I'm sorry about it. I don't know if you received my email or not, but because I have like this severe sore throat, so I couldn't come to class, and so that's why it's completely online. And we haven't covered much until now. I was just repeating what we already did last time. So we came up with this like state value function last time, and we came up with this like state action value function. And the whole point of solve, so we are trying to find the best policy, right? So what should be the best policy for my agent when taking any action? So that's an optimization problem that we solve in reinforcement learning. And we also formulated our entire process as an MDP, which was a Markov decision process. So today we are just looking at what is like this optimal, how can we come up with an optimal value? What should be that optimal value? How to solve that using dynamic programming. And all of the material is derived from the textbook. So in specific, if you're interested in like going into the details of all of this, it's chapter 2 and chapter 4. And I have provided the link to the book. So it's chapter 2 and chapter 4 where we solve an MDP using dynamic programming. So that's all we are doing. So I just like read or repeated what we said last time. So this is my value and this is my the expectation equation for my state action pair and my state value equation. Okay. So having said that, let's like further try to understand this Bellman expectation equation for the state value function. And the book talks about something that's known as a backup diagram for um, state value function, which is like the first one. And then it relates that state value function to my state action function through a diagram because it's easier to understand what's really going on because we need some way to create a relationship between this and this, right? So some direct relationship between the value and given like some action is taken by my agent and this is the value. Okay, so let's try doing that the way, like, obviously I derived it from the book. So let me draw it here, or maybe there is some more space here and draw it here. So what's going on is, and this is known as the backup diagram according to the textbook. I didn't make that up. Let me write it down. Backup diagram for state value function. And we'll see like this is also related to the state action as well, right? So let us say that we are in some state, and this is like a computational diagram to represent like the sequential process that's going on. So let's say this, I'm in state S, and so the value that I get being here, right? So this diagram actually is a representation of the value of being in a particular state, right? So we denoted by this V sub pi. That's what at least we decided last time. Okay, so my pen stopped working. Just give me a second. Okay, why is this? Okay, strange. Let's do that again. Okay, I'm sorry about this. I don't know why this is happening. Is it because of... Okay, working again. So some magic happens. I'm not sure exactly what, but yeah. So going back to my computational diagram that helps me understand this backup diagram. So let's say I'm at this node, which is just like giving me that there is some state S and I'm at this state and the value that I'm getting from being in this state is this V pi S. And then from that particular state, I can take some action, right? And I can move to some other state. So there are a lot of actions that are available for the agent. So remember the vacuum example that we talked about last time. So my vacuum can move like forward, backward, right, left, right. So lots of actions. Let's say there are 2 actions available. And the way the book describes these action nodes is by using these black, I don't know, circles. So I'm just like using that. And let's say I choose this action A, right? So this action A is like leads us to get this Q value, which we've defined earlier, right? And so there is this like Q value or state action value function for each of the action, right? So for every action we have this. And the best like we can do to create a relationship between my V and my Q is that I can do an average of all the Q values, which will give me how good it is to be in a particular state, right? So basically I can define my V sub pi of S using all of those like actions. Let's say I had like another action A prime here, and maybe I had like other actions available as well. So what I can do is I can create a relationship between this V pi S and Q pi S by just saying that my V pi sub S is like summation of all the actions, or like the average rather, and where this is the probability of under policy pi taking action A in state S. So we defined this last time, right? So this is the policy, which is usually a probability, and then the QS A, which is this, right? So we can come up with this like equation. So this equation gives us the connection between state value function and state action value function, right? Now remember, like we're not done here, because at every state I have like this whole set of actions that I can take. And then eventually I move to some state S prime, right? And so what actually needs to happen is that there is another like addition to this backup diagram where we will connect it to the next state, which is like my S prime, right? So basically, like to summarize, suppose like we start off by taking some action A. Now, because of this action A, the agent might be stepping up in like going to some other state S prime. So my question is, how good was it to take action A, right? So that's what we are trying to answer here. So one way is like we can average these state values of all the states added with an immediate reward, which will tell us how good it is to take an action, right? Because I really want to know if I am in like this, if I'm moving towards some other state and I'm taking some action, I really want to know how good it is to take a particular action A in state S. So we defined some of it like very simply last time, if you remember, but I'm going to redefine it. And I'll say that this is how good it is to take action A. So this is what this Q is telling us. The Q value actually tells us how good it is to take action A when I am in state S. And that is equal to my immediate reward that I get being like moving from state S to some other state and taking action A, right? So again, we defined it last time, plus the discounted value times the summation of all the other rewards in future. But remember what happens in future? We were also thinking about the transition probabilities, right? So I'm going to bring that equation here in again. So again, you've seen this before, but I know I'm repeating a lot of that, but we need all of this. So let's say this is the transition probability moving from state S to S prime for taking action A, and then this is multiplied by V pi S prime, right? So these two equations are actually telling us like how these are related to one another, where P is like the, again, the transition probability. This P S prime, which we defined last time, is the transition probability of like moving from S to S prime. So that's it. So what's actually going on as we are moving from one state to another in like this entire MVP is that I'm here in state S, and then I take some action A, right? I get some reward, sorry, small r, let's say I'm denoting it by small r, and then I move to another state S prime. So S prime, that gives me this value at S prime, right? So this goes on, and again, like I'll have a set of actions, and then I'll have the Q for that S prime, and so on, right? So to summarize, let's say my agent is in some state S, and And from that state, let's assume our agent can take, like, let's say only 2 actions. And then based on like one of the action that I chose, I will get into state S prime. And the probability of the action my agent might take from S is weighted by our policy. And after taking that action, the probability that we land in any of the S prime is weighted by the environment, right? So weighted meaning the probabilities that are coming into picture. This probability meaning weighted by policy. This transition probability meaning the probability that I am going from one state to another. So that probability is given to us by the environment, right? Okay, so having like defined this and having like defined this entire diagram, because that's how this moves. And again, you'll have like these black dots, and depending on the number of actions you can take, this is what we are looking at right now, right? So mathematically, first of all, we've come at a point where we have a relationship between V pi S and Q pi S. That's one thing. And then the other thing is that we have some recursive kind of a relationship just by looking at this diagram here, right? We have some recursive relationship that exists within like the state value function and the state action value function, right? So I'm going to write the recursive value here, and that's again given in the textbook. I have like copy pasted that here, this entire equation, but after looking at the graph or the computational graph that we looked at, now this will become clear as to like how we got here. So I'm going to rewrite all of this. Let's see how we got here. So the first thing is that mathematically speaking, if we are at some state S, that is actually the probability of some policy, remember, times the immediate reward plus the discounted value of the transition probability times the value that you derive being on the other, what do you call it, state. Okay, so what does that mean? So this is exactly what I'm talking about, right? So we know what this is. This is the probability of following some policy, right? So that's what we said, weighted by policy when we say that, right? And then this was the reward R that we got in our like picture or the diagram that we were just drawing. And then here is the discount value. And this here is the transition probability, right? So this is the transition probability. Okay. So because like we are interested in finding out how good it is to be in state S after taking some action and landing on another state S prime under policy pi, right? So that's why we are able to define or describe this value function as something like this. And let me write it in like the notation that we came about last time, is that we have like all these actions that are available to me weighted by the probability of following this policy pi times the immediate reward that I'm getting plus the discounted value of like all the future states time like multiplied by their transition probabilities under action A V pi S prime. So this is the exact equation that's like these two are the same equations, right? So the book like takes a different notation for transition probability. We just like summarized it or like we denoted it in a different form. So this is a recursive way of denoting my state value function. And similarly, I can have a recursive expression of my state action value function from the backup diagram that we just saw, right? So let me rewrite that here again. And again, the book actually describes that in greater detail, but I'm just like highlighting the important points. So the Q function and the V function both have a recursive form. That's the fundamental idea that I'm trying to emphasize here. So again, the Q, which is the state action value function, is the immediate reward that you get after like following or after taking action A, plus like gamma discounted value summation the transition probabilities, because that's what we defined last time, times the and so here was a Q, right? So I would just like replace the Q with the probability of following a certain policy, and then the Q that I'll get when I'm in state S prime, right? So this bracket here will have like a very similar kind of a structure, Q pi being in next state. So basically, this entire thing is coming from the fact that the backup diagram was like repeating itself again and again. So you'll have like a Q pi, and then you can like derive this value from there, right? So basically we have these two equations. So that's the whole point. Like, of course, if the math is overwhelming, that's fine. The whole point I'm trying to make is that mathematically we can express the state action value function and the state value function like in a recursive fashion, right? Where they are the sum of the immediate reward times maybe some probability plus like the discounted value of what you're going to get in the future. Okay. So all of that is good, but now we have to define the optimal state value function, right? I know that this is the value I'm deriving for being in like state S, but what like in an MDP environment or like the Markov decision process that we followed in order to derive the value and the Q value, right? What is the optimal value function? Right? So that's the next question that we are going to answer. And like, if there are any questions, you can just type in the chat. Like I'm just talking and talking and let me quickly see. Okay, that's fine if there aren't any questions, but like, just remember the high level. And as I said, I've taken all of this from this book, right? Chapter 4, dynamic programming, and chapter 2 in this book. And I provided the link. So just in case you want to go over that again. So coming to like this optimal value functions, what exactly is an optimal value function? So we will, because we have these two equations and we'll just like focus on these two equations, right? The Bellman expectation equations that we have. So the optimal value function or the V that we have, right, is the one which will give us the maximum value compared to all other value functions. It's as simple as that. So when we say we are solving an MDP, it means we're finding the optimal value function, right? So again, the way the book defines this optimal value function, and I'm going to write that again here, is let's say we denote that optimal value function with this V star, and we say the if under policy pi, this is my like the maximum the value function which yields the maximum value compared to all other value functions. As simple as that, right? So this is my optimal value function. This is what I want, right? So V star tells us like what is the maximum reward we can get from the system, and that's what we are after, right? So obviously once we have that, and because we are like looking at every state, at every reward that we are getting, from the perspective of both the V and the Q function, right? So I'll also define my optimal state action value function or my optimal Q function. And similar to my V function, my Q function is telling me that my optimal value is when I get the maximum reward when I take an action A and I move from state S to S prime, right? So the only thing that gets added from V to Q is the action part, right? So that's one easy way to remember that. So that is max over some policy pi S comma I, right? So very like straightforward. Yes, of course, like I'm interested in finding the optimal value, but what optimal value? Well, optimal state value function and optimal state action value function, right? And then you must be noticing that there is this like pi in both the equations, right? And so pi is the optimal policy because that's important, right? It is under some policy. That means I'm following some rules from that policy to take an action, right? So I have to, whenever I'm solving this MDP for optimality, I have to consider optimal policy. So I have to define optimal policy, and I need to understand what is meant by an optimal policy. Well, like as the name suggests, and as like the book talks about it, I think I wrote it here. Let's quickly check. Yeah, so here it is, right? So the optimal policy is one um, which kind of results in the optimal value function. And we just defined an optimal value function, right? So the optimal policy is the same as the one that gets us the best value function, or and the optimal state action value function. And we'll see going forward that it's one and the same thing. Whether you're getting the best V is actually leading us to get the best Q. Okay, so that's what the optimal policy is. Mathematically speaking, we can say that it is like of all the policies that are available to us, it is the best in the sense that, like, this is how the book writes it. So I will also write it mathematically here. That let's say my pi is my optimal policy. So that means it's at least greater than or equal to some other pi prime if my value function for that under that policy is greater than or equal to my value function for that pi prime, right? For all s, for all the states, right? So that's what my optimal policy is, right? And one thing to remember is that under an MDP, I can have more than one optimal policy, right? And the good thing is all optimal policies, they achieve the same optimal value function and same optimal state action value function, right? So all of that is good. That has been proven. And of course, like the book talks about that in detail. But let's actually focus on one thing, that is like, how do we find that optimal policy, right? How do we find the policy under which my value is going to be maximized, or my Q value or my Q function is going to be maximized, right? So we can find that, let me just quickly see if that's, yeah, so yeah, so that's the next thing that we would try to do. And we'll be solving that using like dynamic programming, and I'm going to come to that. But let's like formulate that a little bit, because like the book formalizes the like how do we find an optimal policy. So I'm going to do that as well. So think about it. We are finding an optimal policy by maximizing over my like all Q values. That means all my optimal state action value functions. And so I'll solve for my best Q value and then pick the action that gives us the, like, that gave me that optimal state action value function. So mathematically speaking, the way it can be described is like this. And let me quickly write it down. It's pretty simple. Like it's nothing. It's not something difficult to understand. So this is what an optimal policy looks like. And remember, we are talking about like MDPs throughout. I'm not deviating from that. So let's say pi star is my optimal policy. And of course, there's the state action mapping. And this is 1. If my action is 0 otherwise. Okay, so what this is saying is that for a state S, I'll pick action A with probability 1 if it gives me the maximum like Q star, and this Q star here is the best or the optimal state action value function, right? And so if I know that best Q star SA, I can get an optimal policy from that. So basically, I think that we are just like rephrasing the whole thing in a different way, right? So that's what we're doing here. So the question arises, how do I find that Q star SA value, right? And so remember, like all our discussion about Bellman equations, that comes back here. And so we can do that. The optimal value function, which we are interested in finding, is recursively related to the Bellman optimality equation. And now you must be wondering, what is this Bellman optimality equation? Because until now, I've been talking about Bellman expectation equation only, right? I've been talking about Bellman expectation equation, and then I came up with the V's and the Q's, and I said that this is the expectation equation. Now, the only subtle difference between the expectation equation and the optimality equation is that, remember, I was summing up all the probabilities of basically I'm taking the average of the actions that my agent can take, right? But instead of doing that, I'll take the max value, the action that will provide me with the maximum value, right? So if we think about the backup diagram, the only thing that changes there is, like, remember we had something like V S, and then we move to some Q, S, and those were like the average values. So depending on QSA, right? Cannot be QS because I'm taking some action A, and here like I'm in some state S. The only thing that changes here is that let's say my agent is in like some state S, and it can take like two actions, A and A prime. So I look at the action values for each of those actions. And instead of like taking the average, remember I summed them up and then multiplied the probability value with the actual value. I'm going to take the max Q star value. And so that's why like the star comes in. If I'm taking the max value, the star comes in. So mathematically speaking, my V star S is going to be, instead of being the average, it's going to be some max, that like something that makes this the max, right? Some action that makes this the max. That's it. Like instead of taking the average of all the actions and going forward, right? So similar to this, like I can redefine the Bellman expectation equation for the state action value function. Remember the Q? I can redefine it by just saying that instead of like, instead of taking the average of the values of all the states, right? I am just interested in the optimal values of every state. So again, I will just like do a slight update in the equation that I already had. So as long as you're okay with the earlier two equations, the V and the Qs, we are just like making small updates here, right? So instead of like having the average probabilities and everything multiplied, now my optimal Q star value is going to be R, the immediate reward, plus the discounted value is, I think it was this, the transition probability, and then V star S prime, where V star is defined like this. So again, the recursive relationship in some ways is there, right? And then we are not averaging, so we are not like another way of thinking about it is like, let's say my agent is in S, and from that it took some action A, where the probability of taking that action was weighted by the policy. And then because of that action, my agent is now in S prime state, where the probability was weighted by the environment. And then in order to find the value of state S, I'm not like averaging, but I'm finding the max. And then I am eventually like averaging the optimal states of my state S prime, right? So, okay, what does all of that mean? Right, so again, I will rewrite the equation for my V star. Sorry, that's a bad star. S as being the max of RSA plus gamma times the summation of, and I'm not repeating the summation because like we know that, transition probability V star S prime, right? So that's the only change that happens. And then similarly, we can like understand that this like Q star and the relationship between V star would be like similar to what it was earlier, except that instead of like having the average, right? And again, like I'll rewrite all of that. So this is coming from our diagram, right? Equals the immediate reward that I was getting times the discounted transition probabilities for action A, and the max of my Q star S prime, A prime. Remember, it wasn't the max earlier, it was the average. Like we were summing up over all the probabilities there. So now we're not doing that. We are taking the max of Q star. So the only thing again that remains with us is this like V star and Q star, and then their new definitions of like their new definition in terms of like I'm selecting the action that maximizes my value from like taking that action. So that's the only difference between Bellman expectation equation and Bellman optimality equation, right? So once we have the Bellman optimality equation for an MDP, which is the Markov decision process, we can use dynamic programming algorithms like policy iteration to solve this. So the book actually describes two different ways of solving these Bellman optimality equations, and I can quickly jump to that. So here we have the Bellman optimality equations, and the first technique of solving this is through policy evaluation. And like primarily speaking, it uses an algorithm known as policy iteration. So that's the only one that we're going to look at, because I know that this is like quite overwhelming, so much information. And one thing that I would like to point out here or emphasize is you don't have to remember all the derivations that we did, as long as you understand how the relationship between V and Q works. And the other thing is that there is a recursive relationship. And as we are moving from one step to another, we are following some kind of a greedy approach, right? So we are following this approach wherein we are trying to maximize the value we are getting from taking a certain action. So those are like the key takeaways from like deriving. You don't have to remember the entire derivation of how we got here, right? The optimality equations. Okay, so before we jump into any of the solution approaches, I will quickly go back and think I talk about, yeah. So this section here talks about like solving MDPs using dynamic programming. And I'm sure you're familiar with dynamic programming, right? Is everybody familiar with dynamic programming?
Yes.
Is okay. Like if there's someone who's not, then I can point you to resources that you can look at, but I'm guessing everybody mostly is. And so just like a quick overview, so dynamic programming is like a divide and conquer approach, right? Which is essentially we have a problem, we break it down into smaller sub-problems, and instead of like solving them independently, we take the results of those like smaller problems, and then we can use them to solve the bigger or the larger problem, right? So then like the only thing that we need to remember is that when we are using dynamic programming as a solution approach to solving any problem, there have to be like two things, and I've listed them down here, right? So these two things are important, that the problem should have an optimal substructure, right? So this means that a problem can be divided into subproblems, and if we find optimal solutions to these problems, then we can use that optimal solution to find the optimal solution for the bigger problem, right? So you must be familiar with that as well. And then overlapping subproblems, right? So like obviously if you solve it for a smaller problem, that's what it means. You don't need to solve it again and again. Okay, so why is like dynamic programming so important when we are talking about an MDP, right? So if you remember, and I think I've been emphasizing that a lot, that the structure of these equations that we came up with is somewhat like recursive, in the sense that, of course, I'm trying to solve this V star of S. So I'm trying to find the optimal V star and the optimal Q star. But that is somehow related to the optimal V star for the other states. For example, here state ST plus 1, right? Similarly, this optimal Q star is related to like the Q star of state like ST plus 1, and so on. So, right, so there is this like recursive relationship, meaning that I'm like solving that problem again, maybe for another state, right? So what the point that I'm trying to make here is that this Bellman equations, they have like, we can break this down and find the value function for like some subproblem, and then use that to find the solution for like the rest of the problems, right? So basically the notion of solving MDPs, when we are trying to solve an MDP, what do we mean? Well, let's go back to the lecture notes. I think I did put that down. Okay, yeah. So that question also comes a lot, right? Like when I say I'm solving a Markov decision process, what exactly am I trying to do? Well, remember the whole point of spending so much time on getting the value equation and the state action equation, the V and the Q, is that I'm trying to find the value function that satisfies my Bellman equation. And once I've found the optimal value function, then I can use it to find the optimal policy, right? So I define the optimal policy as the one that has the maximum value anyways, right? So they're like some ways saying the same thing, right? And so when I'm solving for an MDP, I can break it down into two parts. And that's what those two parts are. The first one is prediction, and the second one is control. So in prediction, last time we defined an MDP as something like this, right? It's characterized by S, A, P, R, and gamma. So if you remember, S was like the state definition. A was the action, like all actions that you can take. P defined the transition, the model through which we are getting the transition probabilities. R was reward that you're getting, all the rewards that you're getting, and gamma is the discount factor, right? And given some policy pi. So my job in my prediction, when I'm doing my prediction, is to find the value function by evaluating a policy using the Bellman expectation. Some internet issues right now. Let's see. Can everyone hear me now? I think I'm having some internet issues at this point.
Yes.
Okay, and I did cut out in the middle, right? Okay, let's I don't know where it stopped working because WebEx was just throwing some errors. So going back, what I was talking about was what is this notion of solving an MDP? Well, the notion of solving this MDP can be broken down into two parts. The first one is prediction, the second one is control. So prediction, well, I'm trying to find the best value, right? Using my Bellman expectation equation. And then the second one is control. So that means I'm trying to optimize the value function that I calculate during the prediction process. That's part one. So I can find the optimal value function and optimal policy for my MDP. So that's what this is. And there are two algorithms to solve this, right? So there are two algorithms to solve this, and both are described in the textbook, obviously. The first one is policy evaluation, and then the second one is value evaluation. I do mention value evaluation or value iteration. So the one that we will focus on, we'll focus only on one of them, which is the policy evaluation that involves something that's known as policy iteration, right? I know that's a lot of information thrown here. So let's reevaluate what we are doing. So well, we are trying to find the best value using my Bellman expectation equation for my Markov decision process, which I have defined using these parameters, right? Given some policy pi. And once I get the best value function, I can evaluate a policy because I can use the Bellman expectation equation to see what is the expected value for that policy and then do something with it, right? So that's the idea behind policy evaluations. So what we are going to do is we will utilize something that's known as synchronous backups. That's what the book calls it. And so it means that we are going to take into consideration every state in my MDP for calculating the value of a state. Okay. And so that's the idea that has been borrowed from dynamic programming, where I will take into consideration all the states and calculate the value for state. And then why is it known as policy evaluation? And for some reason, I don't know why I didn't write it here. Let me write it down. Okay, let me go down. Okay. So again, let me just reiterate everything and put everything together. So now we are trying to find my optimal policy, and I'm using under this Markov decision process, right? That's how we came up with my V and my Q. So under my MDP, what I'm trying to do is I'm using dynamic programming to solve for my optimal value and get the optimal policy. And under this, there are two algorithms. The first one is known as policy iteration or policy evaluation. And the second algorithm is value iteration or value evaluation, so value iteration. And this, if you're interested in this, you can read it from the book. I can give you a high-level idea of how this works, but we will focus only on this, only on policy evaluation. How can we use policy evaluation to solve for my best V? Okay. So now going forward in policy evaluations, I'm utilizing something that's known as synchronous backups. Meaning that I will take into consideration every state in my MDP for calculating the value of a state. So then where does this policy evaluation come in? Because this is the technique or this is the algorithm that we are following. So policy evaluation basically means like we will try to find out how much reward our agent is going to get by following a particular policy pi, right? So that's what we're trying to calculate, and then we want the best. So we want the most reward, right? So we want to evaluate a policy pi, right, and see how much reward my agent is going to get. And the way I'm going to evaluate my policy is that I will compute the value of being in a state, right, using Bellman expectation equation. Because with the Bellman expectation equation, I can tell how much my agent, how much reward my agent got under policy pi. So if you remember, and like at this point, I just like remember this very much because I wrote that equation so many times. So I'll like rewrite it here. So under policy pi, let's say some policy pi, which using which I will like come up with these probabilities or whatever these values are, and I'll evaluate my V, right? So for all actions, the immediate reward plus the discounted future rewards is prime, and I'm just assuming that I know the transition probabilities somehow, right, of moving in the state as prime. So this was the equation, the Bellman expectation equation. So now, so how do we evaluate my pi, right? Okay, what happened to the mouse? Well, to evaluate a policy, I'm going to use this equation in an iterative way. So what does that mean? Well, I'm going to use it in an iterative way, and I'm going to add some iteration number k. So k plus, let's say this is k plus 1 because I'm going to show you an example here. So this is the iteration number. And let's say I want to evaluate this policy pi, and like the whole notion of evaluating this policy pi means how much value am I deriving from being in state S, right? So I will calculate the value of the next state by backing up the value of the current state from the previous iteration. Okay, so let's see what that means. And somehow I want to write it here because then it will become clear. So let's say I am here. Remember our backup diagram. So S state meaning I have some value S. And let's say this value is from the k plus 1th iteration. And remember, like in every iteration, you are going to get all the values. So how do you compute it for like the k plus 1th iteration? Well, you took some action A, and of course, like you have the Q and everything, and the reward R, and then you move to some other state S prime, which led to like Vs prime. Now, if I'm computing this like at the k plus 1th iteration, I'm taking the value of V from the previous iteration. That's what this is here. Like notice the k here, right? So this is how we're doing it iteratively, right? We're calculating the value of the next state by backing up the value of the current state from the previous iteration, right? So basically, if you look at the root node, if like this, I'm calling this the root node, right? This root node is like given by the reward I got by taking action A plus the value that I have in state S prime, right? And so we are using Bellman expectation equation in an iterative way for this dynamic programming type setup, right? So basically we'll use the value of the leaves, which is like S prime here, that's my leaf, from the previous iteration, right? When we were computing the value of state S last time to calculate the value of state whatever, like S prime, right? So this is going to go on and on in every iteration, right? So for the second iteration, for example, I'm going to use the value of state, which I'm computing right now, which is k plus 1. So in k plus 2, I'm going to use the value from the previous one, and so on, right? So how does this all like come about? I remember there is a nice example in the textbook, and you can quickly go over that if you need an example So this is the iterative policy evaluation. This is how the entire algorithm runs. And I think high level, I talked about it. So we are not going to go into this. But this example here gives us a good overview of how this works. So basically here you have like these different states and the agent can move like either top, bottom, right, and back. And there are some transition probabilities that are given, and like how can we calculate the value from every step, and then that's how we move forward. So this is like a nice example to kind of demonstrate what I just like described, right? So now coming back to, so you can just like go over this example 4.1 to better understand like with numbers what's going on. So now coming back to the big question, like what is the optimal policy? Like, of course, I'm iteratively going over like all possibilities, right? So basically this algorithm, which is known as the policy iteration algorithm, it breaks this entire process into two parts. So basically, first we evaluate a policy using Bellman expectation equation, as I just described, right? And then I act greedy to this evaluated value function, right? So act greedy means I greedily pick the value function that gives us like the optimal, and believe it or not, this greedy approach gives us the optimal policy, right? So what exactly this idea of like policy iteration is, and how are we like getting to the final optimal value? Well, I'm doing two things. So let's write it down here. So I'm doing two important things. Just give me a second, I'll grab water. I'm sorry about that. So the idea of this policy iteration, as the book describes, and I'm just like summarizing that here, is that you have like this V pi S, which like the value function calculation happens. So that's step one. So you evaluate your policy pi using this like whatever the equation was for the value function. And then in the second step, you act greedy to the evaluated value function, which yields a policy better than the previous one. So we do follow under this algorithm, we follow this greedy approach, like the new pi prime is going to be the greedy V pi, like the max that I get, right? So we keep iterating through these two processes until it converges to my optimal value function and hence my optimal policy, right? So believe it or not, like this, and there is an entire like mathematical description of why this is an optimal policy. Well, like high level, if you're evaluating this policy, calculating the value function using Bellman expectation equation, I'm acting greedy to that value function. And because I'm acting greedy, it makes my policy deterministic in some ways, right? So basically what I'm doing in every step is that, like, let's say I begin with some random policy, I evaluate that policy using the Bellman expectation, right? Step one. And then I act greedy to the value function that gives me a new policy. And then I keep doing that, right? I keep like continuously doing that. And then when we do that for an MDP, that results in an optimal value function. So that's all that is there to this policy iteration algorithm, believe it or not, right? So acting greedy means that I pick an action, like let's say A, that would yield me the maximum value in a particular state. So basically when I acted greedy, this is what happened, right? So I picked up, like, I came up with some value which actually led to this. Right? So this is my greedy policy, and that greedy policy, when I keep following these two steps again and again, it eventually converges to the best one, right? So why this like Q pi SA? That's because, like, remember, like the definition of my Q value function, the definition of my Q value function is that it tells me how good it is to take an action in state S, take action A in state S, or like how much value I'm going to get by taking action A in state S, right? So then if I'm taking this R max over this Q pi SA, that means I'm picking the actions in state S that maximize my Q value, right? Or that gives me the maximum Q value. So the only thing that remains here is that, like, why is this, like, that question must be coming to your mind, like, why is this greedy policy making my policy the best? Like, why is it optimal? So there is a complete mathematical proof that, like, we can go over quickly, that shows us that, like, this is eventually the process of selecting greedy approach in every step is actually leading me to choose the best action that can be taken at that state S, right? So recursively you can actually show that, like, basically high level, what the proof that the book gives us is that this, like, let's say we pi S, let's say I'm taking this step, like the value can be up. So this thing is actually telling us that, like, if I took the greedy step, right, uh, it in it is in some ways leading me to, because the greedy step is a deterministic step, right? So in some ways, if I was like taking the policy that led to the max value is in some ways at least equal to or better than following any policy in, like, random, right? Or like just following the same policy again and again, right? So basically saying that the value that you get from policy pi is at least less than or equal to, like, the Q value that you took under pi prime S, right? So let's go over, like, how they show that this is the case. Actually, I think it's right here. Um, yeah, so here we are able to show that, like, if we were following policy pi, right, and then using the expectation equation, if we keep, like, like, basically if we can apply the same idea and again in the same step, we can show that, like, this is at least equal to or less than the pi prime or the greedy policy that I've been following, right? So that's what this entire, like, discussion here tells us, that the greedy policy in fact does lead us to the optimal value. Okay, so then they also talk about some, like, modified policy iteration in which, like, when should we keep doing this iteration, like when should we just go on and on, or should we stop at some time? So that's the modified policy iteration. I think there is a section on that, how the policy iteration happens and how do we modify it. Yeah, so because, like, a finite MDP has only a finite number of policies, this process must converge to an optimal policy and an optimal value in a finite number of iterations. So that's what happens. You don't have to, like, go on forever. That's good news for us. And also one thing to remember is, like, what is this, like, principle of optimality? So I have listed that down here. Principle of optimality, or, like, what is this optimal behavior? Because we are saying it converges to optimality, right? So here we are defining the optimal behavior. That means an optimal policy is divided into two components, an optimal first step, and then following the optimal policy from the next step. So that's what we call the principle of optimality here. All right, so that was the only algorithm that I decided to cover in order to solve this MDP. And this is pretty straightforward. All you have to remember is these two equations and then the policy iteration algorithm that just, like, keeps greedily picking up the best policy and then eventually, like, converge to optimality, because, as I said, MDP has finite number of states. However, there are other ways of solving this, and the other one is this value iteration. In this algorithm, so for example, in policy iteration, we first evaluate a policy, find a value function, and then act greedy to construct a new policy, right? But in this one, we do not compute policy for every value function. Once we find the optimal value function, we compute the optimal policy from our final optimal value function. So let's not go into, like, too much details. If you're interested, you can definitely go to the source and read that. But yeah, that's another way of, like, getting the best, like, I would say, value function and getting the best policy, right? So there are a few other dynamic programming algorithms. If you just go to, like, chapter 4 here, you will be able to look at it. Chapter 4 is dynamic programming. And so today's lecture was mostly extracted from chapter 2, sorry, not chapter 2, 3 and 4. So if you're interested in this value iteration, you can go and read more about it and the other, like, details of the dynamic programming algorithm. Because I just figured that we might not need to go into too much details of that, as long as you understand how we are getting the value function and how we are getting the state action value equation. So I would just like stop here and like next time I would start with how can we use reinforcement learning with along with deep learning, because that's the whole point of like showing you what reinforcement learning is, what are some of the ways of solving reinforcement learning type problems, and how can like why does deep learning, why is it so effective with deep learning, right? So you understand that this is a completely different paradigm of learning. And next time we will begin by looking at how can deep learning be utilized along with reinforcement learning to solve more complex problems than just like this MDP that we looked at in this lecture and the one that was earlier. So yeah, that's all I have for today's lecture. If you have questions, you can stay back and ask. If not, then that's it. And yeah, in terms of announcements, one like part of the assignment 5, I think, was remaining for 6,000 level students. So that will be released sometime today, and that would most likely be related to reinforcement learning. Okay, so that's all I have for today. I'll just stop recording. Yeah, thank you, Stephen.